In the following example, we are asked to find the area enclosed by the given curves. Now, I've been nice enough to supply you with a graph in this video, but you're not always supplied with the graph. And in this question, it wasn't intended to have a graph. So the idea here is that you need to find the intersection of the two curves in order to figure out the limits of integration. Well, this problem is really nice because what we need to do is find this area here that I'm shading in, and that is the area between the quadratic and the line. And so it's easy to see that the quadratic is greater than the line in terms of its y value. And so when we integrate it, we're going to integrate it between the two boundary points there, the two intersections. So in this case, from -2 to 2. So I'm going to integrate then from -2 to 2 the function above, which is 2x minus x squared, and I'm going to subtract from it the function that is below, which in this case is 2x minus 4, and we're integrating with respect to x, so we denote dx. So some simple algebra takes place at the very beginning, and that is to say that we distribute and combine like terms. So we have 2x minus x squared minus 2x plus 4. And when we combine those like terms, we end up seeing that we cancel out our 2x's, and we are left with simply the integral from -2 to 2 of negative x squared plus 4. A very simple integral, if you ask me. All right, let me fix this integral symbol here. It didn't look like one. Okay, so now we're ready to take the antiderivative, and that is we get a negative x cubed over 3 plus 4x, and again we're evaluating from -2 to 2. And so what we do is we plug in these values. So let's take a look. We have a negative 2 cubed over 3 plus 4 times 2 minus, and in this case, I'll put the square bracket again, just to stay consistent, a -2 cubed over 3 plus 4 times -2. We get something that looks like that. And then what do we end up with? Let's see here. 2 cubed is 8, so a -8/3 plus 8 minus, let's see, what's that? -2 cubed is again a -8, negative, positive. So a positive 8/3 there. And we are going to add or subtract 8 rather. And so we end up with -8/3 plus 8 minus 8/3 plus 8. And we get something like -16 over 3 plus 16. And when you do the sum total of that, you get a fraction 32 out of 3. And that right there represents the area of that shaded region in yellow. Okay, so again, nice problem here. Applying this concept of finding the area between curves. Again, the graph wasn't supposed to be supplied. I've supplied it so that you can see the intersections and so that you understand what the limits of integration are. So now let's take a look at another one, slightly more complex, but only because you have to visualize the areas, the two separate areas. So let's say we're finding this area here in yellow, and then we'll be finding this area here in green, and then we will be combining those two areas at the end of this. Okay, so I have supplied you with the graph, the intersections, of course. This is the point, of course, the origin 0, 0, where we have another intersection. So we are going to be taking a look at this from two perspectives. The first perspective is that we need to say, well, x cubed here is on top, and below we have 4x, and then on the top over here we have 4x, and below we have x cubed. So you've got to look at it from the two sides here. And believe it or not, this one I believe is symmetric. So, you could actually just double the area, but let's just go ahead for the sake of the procedure. We're going to integrate both sides. Okay, so let's see. The first integral should read, we're looking at -2 to 0, and we're going to have x cubed in this case minus 4x, a very simple integral here, plus the second integral will go from 0 to 2, and in this case it's going to be 4x minus x cubed because of the way that it is positioned and laid out on the graph. Okay, but now we're set to take the antiderivatives here. We say first x to the fourth over 4 minus 4x squared over 2, evaluated in this case from negative 2 to 0. And then in the second, we're going to have 4x squared over 2 minus x to the fourth over 4, evaluated in this case from 0 to 2. So it's always nice to have those zeros in place because a lot of the times it just makes everything 0. All right, but we're going to go ahead and clean this up one more time, reducing the fractions here. We get x to the fourth minus 4, x to the fourth over 4 minus 2x squared, again evaluated negative 2 to 0, plus 2x squared minus x to the fourth over 4, evaluated from 0 to 2. And so we get something that looks like this. You plug in the 0, you're going to get 0 minus, and now we're ready to plug in the negative 2. So negative 2 to the fourth over 4 minus 2 to the 2 times negative 2 square. We've got that right there. Now we're going to add the second part. We don't need to plug in the 0, but you'll see what we get. You get 2 times 2 squared minus 2 to the fourth over 4 minus 0, because plugging in 0 just yields 0 for all of that. Okay, so really nice here. Not much more to do other than the simple arithmetic, but I think that probably will give you the greatest problem, not the calculus. Calculus here is easy. So we end up with something like 16, the opposite anyway of 16 over 4 minus 2 times 4, plus, and in this case it's, let's see, 2 times 4 minus 16 over 4, which again you can reduce all of that. So you get in this case a negative, and then it's 4 minus 8 plus 8 minus 4. All right, you get a negative 4 plus 8 plus 8 minus 4. And you combine all of that good stuff. What do you get? You get 4 plus 8, which is 12. 12 minus 4, which is 8. Our final answer for our area between the two curves here. And so it was actually really nice. Again, by symmetry, you could have just integrated like one of them and then just doubled the area. It wouldn't have been a big deal. But I think you needed the experience in seeing how to operate here. So as always, I hope this video was helpful, and if it was, remember, like and subscribe.